Okay, so we were discussing the Stern-Gerlach experiment, which told us that, at least for the silver atoms, and we will see later on that in general, for more general systems, to describe the spin property, it's enough to have two states only, two kets, and which we chose as the states that are splitted into that are chosen by the Stern-Gerlach experiment with a magnetic field in the z direction. Well, what is the z direction? Arbitrary. You just choose one direction, call it the z direction, put a Stern-Gerlach experiment whose magnetic field is in that direction. It will split the silver atoms that are created in an Hour1 into two. One of them we call the state of one of them we call the plus, and the other one we call its state minus. We describe their states as these plus and minus kets. Then, of course, there was the problem, what about if we put a Stern-Gerlach experiment in the x direction? The observation tells us that in such a case, for example, if we choose the plus state using the first Stern-Gerlach experiment, after that we know that all the silver atoms have the same identical state. By the way, just the terminology, we call such systems a pure ensemble. It just states that we have a bunch of particles whose states are identical. So that's why we call it pure. So we create a pure ensemble of plus states, and then we send them through a Stern-Gerlach experiment who has a magnetic field in the x direction. And then it turns out that it also splits into two with equal weights. Now we know that these states, the Sx plus and Sx minus states, we should be able to write them as superposition of linear combinations of these plus and minus kets. And we just interpreted the coefficients in this superposition as the probabilities. So if we have a plus state, the probability that it will be in the x plus should be 50%, and the probability that it should be in the x minus should be also 50%. Or we could have done that the other way around. We first have a Stern-Gerlach experiment with a magnetic field in the x direction. We choose the Sx plus state, for example, and then send them through a Stern-Gerlach experiment in the z direction. And we again see that the split is 50%, 50%. And that tells me that Sx plus state should have 50% plus and 50% minus states. So that tells me that the coefficients in Sx plus of the plus and the minus kets should be 1 over square root of 2, well, basically square root of 1 over 2, because their square is our probability, their absolute square is our probabilities. And since it's the absolute square which is our probabilities, we cannot really fix the phase. It can be a complex number also, with whose magnitude is just 1 over square root of 2. So that is why here we have this arbitrary phase e to power I delta 1. Well, the existence of this phase is not really a surprise, because we also have this arbitrariness in our choice of the x-axis. So we say that we first fix our z-axis. This is my z-axis, let's say. But my x-axis can be any axis perpendicular to this one. So I have an arbitrariness in the choice of my x-axis, which is reflected in this arbitrary phase over here. So essentially choosing delta 1 would correspond to choosing an x-axis, or choosing a reference x-axis, let's say. And once we identify our eigenkets, well, we can straightforwardly construct our operator, the Sx plus Sx operator. Sx operator, for any operator, in fact, if we know the eigenkets, all the eigenkets and the eigenvalues, is nothing but the sum of the eigenvalues multiplied by first the ket, then the bra. So we have h bar over 2. This is the eigenvalue of Sx, and it has the ket Sx plus, the bra Sx plus the other eigenvalue is minus h bar over 2, Sx minus, Sx minus. And we can also express this in terms of the original plus minus states in this form. So you see that in the plus minus basis, the Sx operator is not diagonal. We know the Sz operator. It is plus 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 minus h power over 2 minus minus. This is diagonal. If you start with a minus state, act on it with this sz operator, it stays minus. If you start with a plus state, and if you act with sz operator, it stays plus. If you start with a minus state, act on it with the sx operator. You see the minus state, it is this times the minus ket is 0, so this minus minus is plus, so sx times the minus state is just h power over 2 e to power minus I delta 1 plus state. So it's not an eigenvalue. Neither the plus state. If you have the sx plus, this will be h power over 2 e to power I delta 1 minus. Now, we already knew that plus minus states are not the eigenkets because we had identified the plus minus kets over here of the sx operator. So this is what we had done up to now. Now, any questions up to this point? Now, we will repeat this basically the same thing for the sy. We have the sy plus state, sy minus states. We need to identify these states. So basically, again, we first turn to experimental observation. What we know is if you first pick the sy plus state. How do we pick an sy plus ensemble? How did we pick the plus states to start with? If you want to build an experiment, at the end of this experiment, you want to obtain the sy plus states. How do you do that? No. Okay, this is my oven. Okay, there are no eigenstates over there. And there's an opening in this oven right over here which emits silver atoms with random spins. Now, I want to pick the silver atoms that have the y component of spin plus h power over 2. How do I do that? How do I block them? I use a Stern-Gerlach experiment. Okay, so I have this Stern-Gerlach experiment with magnetic field in the y direction. It splits them into two, sy plus and sy minus, and depending on which one I don't want, I block the one that I don't want. So that's how I construct them. So first, once I construct them, then I can just send them to study its composition in terms of the plus minus states. I can send them through a Stern-Gerlach experiment in the z direction, and observation will tell me that they are split into two equal parts. So I know that the probability of plus states in sy plus and the minus state in sy plus, they are 50-50. The same will hold for sy minus. And just using exactly the same reasoning that we use in sx plus and sx minus states, these sy plus and sy minus states will have exactly the same form. Because you see, in obtaining these kets, the only information we used was the sx plus state had 50% plus and 50% minus. Similarly, sx minus is 50% plus 50% minus. The same holds for the sy states. In this sense, they are identical. Of course, this phase can be different. Let me call that delta 2. So these are the general forms of sy plus and sy minus states. True. Correct. So as your friend points out, we have once we choose the y, the z, then we choose the x. Do we have arbitrariness in the choice of y-axis? We still have twofold arbitrariness. If this is our x, this is our y, this is our z, the y can be in this direction if it's a right-handed coordinate system, or it can be in this direction if it's a left-handed coordinate system. So we have this twofold degeneracy, but definitely not such an arbitrary phase. So this delta 1 and delta 2 should be somehow fixed up to a phase, up to plus minus 1. Sorry, not up to a phase, up to plus minus, up to this twofold degeneracy, we should be able to fix these delta 1s and delta 2s. Well, in fact, one of them we should fix, not the two of them, because you see, if this is the z-axis, the xy axis, we can still rotate them. So there's still one phase, which will describe this rotation of the xy axis, and there will be this plus minus 1 digit ambiguity, which will correspond to either the choice of a right-handed coordinate system or a left-handed coordinate system. But definitely not two completely arbitrary phases. So there is one information which we still did not use. Well, we know that for SY plus state is 50% plus 50% minus SZ plus SZ minus. Similarly, SY minus is 50% SZ plus 50% SZ minus. That information we use, but there is one more information that we know. You see, we already have two bases. We have the SZ plus SZ minus basis and SX plus SX minus basis. These two pairs, they are just, we can use any one of these bases. And we are always talking about the probabilities of SY plus and SY minus in our SZ plus or SZ minus bases. But what about these probabilities? What should this be? Well, you see, we already know that this probability is one is y, one is z. So this is the state that we denote by plus all the time. So here is my SY plus. If I take its inner product with a plus ket, what do I get? 1 over square root of 2, then take the square. So this probability is 1 over 2. Well, this tells me that, okay, so if this is the y-axis, this is the z-axis. But you see, this is the z-axis. Maybe you called it the z-axis, but he called it the x-axis. Nothing should change. The important thing is that these two axes are perpendicular to each other. That is the only important thing, physically relevant thing. What you call them, who cares? I mean, nature definitely doesn't care which name you give them. So basically what we are talking about is if you have the spin polarized in one axis, the probability that it will be polarized in one of the directions in a perpendicular axis is just 50%. That's basically what we are always talking about. Well, y-axis, what we call the y-axis and what we call the x-axis is they make 90 degrees. So that probability should still be 50%. So this information we didn't use yet. So that is what we should use now to be able to fix this delta 1 and delta 2s. So let's see, the Sx plus this is my Sx plus state that we derived on last Monday. Sy plus state is, well, it just looks almost identical, just with a different phase. Let's take their inner product. This is equal to 1 over 2 plus e to power minus I delta 2 minus times plus e to power I delta 1 minus, which is equal to 1 over 2. Okay, plus plus. What is the inner product? 1 plus e to power minus I delta 2 minus plus the inner product 0 plus e to power I delta 1 plus minus 0 plus e to power I delta 1 minus delta 2 minus minus this and this 1. So this is 1 over 2, 1 plus e to power I delta 1 minus delta 2. Or its absolute value should be equal to 1 over square root of 2, or 1 plus e to power I delta 1 minus delta 2. Absolute value should be equal to square root of 2.
Yani aslında SCL plus ve SX plus aynı yaklaşımı kullanıp bunların arasındaki pas farkı artık üçüncüyü belirlesin diyoruz yapmaya çalıştığımız şey. Sonuçta bir arbitrarimiz var ortada ve biz inner product aslında matematiksel yöntemle aradaki feyzi bulmaya çalışıyoruz.
In a sense, yes. Well, you see, there is no okay. So what we need to do, we have some information, some observations we can make, and one of these observations is that what we name certain axis doesn't really matter, shouldn't matter. And so, up to this point, we were always looking at the relation of one axis with the z-axis. So using those information, we said that, okay, the kets, the Sx plus minus, Sy plus minus kets, they have this phase. But there is still one more information that we didn't use up to that point, the relation between the x-axis and the y-axis. That we didn't use. That relation will give us some more information about these kets, which will kind of fix, to some extent, the arbitrariness in the choice of phases. So how do you solve this equation? Let's use some complex analysis, the complex plane, just to interpret what this equation tells us. This is my complex plane. Now, here I'm looking at a number whose absolute value is square root of 2. I know that in the complex plane, all the numbers whose magnitude is square root of 2, they lie on a circle, whose radius is square root of 2. This is minus square root of 2, minus square root of 2, square root of 2, square root of 2. These are all the numbers whose magnitudes are square root of 2. First of all, I know that the number in this absolute value should lie on that circle. Well, what is that number? I have one complex number, 1, This is 1, somewhere over there. To that 1, I am adding some other number, complex number, with magnitude 1. So if I add, well, just you can think of complex number as vectors. How you add vectors, you just put them one on top of the other, the end of one, the beginning of the other one. So this one is this one, this vector. This I can treat it as a vector. I just have to add, starting from here, a vector with unit magnitude. It can have an arbitrary direction. I don't really know this. This direction is given by this delta 1 minus delta 2. So that is my second circle. Since its magnitude is 1, it goes through the origin. That at least I know. So this is my second circle with radius 1. Well, there are two intersection points. One is over here, and the other one is over here. And these, let's say, this is my delta 1 minus delta 2. That phase gives me the angle with the real axis. Well, you see, this is 1, this is 1, this length is square root of 2. So this should be 90 degrees. And similarly, the other possibility is this one. So delta 1 minus delta 2 should be either pi or minus pi. Or each power I delta 1 minus delta 2 should be equal to plus or minus I. Each power I delta 2 should be equal to plus or minus each power I delta 1. Plus or minus I delta 1. So let me go back to my states. I'm sorry, this is, yes. So these are my Sx states. And these are my Sy states. They have almost exactly the same form. Now let me rewrite. Sy plus is equal to 1 over square root of 2 plus minus I e to power I delta 1 minus. And Sx minus is 1 over square root of 2 plus or minus I e to power I delta 1 minus. Well, I still have some arbitrariness. Well, that is kind of expected. I have chosen 3 perpendicular axes. The z-axis is fixed, x and the y-axis, well, I can just rotate them. Still, they will remain perpendicular. And this rotation, we will be discussing them, that this rotation in the 2-dimensional plane is what we call the U1. Basically, you can think of them as rotations on the complex plane. And rotations on the complex plane is just multiplication by a complex number whose magnitude is 1. It is this one. If you multiply a complex number by e to power I delta 1, you just rotate the complex number by delta 1 in the complex plane. So that term over there is nothing but rotations in 2 dimensions. And that is what we expected. The second arbitrariness, this choice of the sign, plus minus. Well, that is also expected. There is one information we have, one choice we make when we are choosing our axis, whether we will be working with a right-handed coordinate axis or the left-handed coordinate axis. We didn't put that information here yet. And if we put that information, if I'm not wrong, the correct choice should be, this should be plus, this should be minus. So this, we will see later on. Can somebody check that this is the correct convention with the book? Nobody has the book?
Yes.
Right. Okay, so is this the correct convention of the book? Can you check it?
No.
Okay. There's still this arbitrariness in delta 1, which we fix to 0. So that e to the power I delta 1, we just define it to be 1. So those are our states. Sx plus is 1 over square root of 2 plus minus. Sx minus is 1 over square root of 2 plus minus. Sy plus is equal to 1 over square root of 2 plus I minus. And Sx minus, Sy minus is equal to 1 over square root of 2 plus minus I minus. Okay, one thing. But if you look at this relation between those two phases, we cannot avoid using complex numbers to describe our system. Now, in classical physics, we never meet complex numbers. They only appear because we want to use some simple mathematical properties of complex numbers, but physical objects or quantities that describe physical objects are never complex. But here we see that we cannot avoid this complex I. Now we have these operators, Sx and Sy. In your homework you will be, we can construct the matrices if you like, or just construct the operators, then you can talk about their commutators, which will be important for us later on. And one of your homework questions should be the calculation of these commutators, starting from the operators. And you will show that commutator of Si, Sj is nothing but I epsilon I j k sk h bar over 2. So just starting from experimental observations, we could construct our eigenkets. From the eigenkets, we could obtain the corresponding operators, and we can derive the commutation relations. Yes? Well, there should be an h bar over 2. You see, S itself has an h bar over 2. On the left-hand side, we have two of them. On the right-hand side, the sk has one of them. The other one should be explicit. Correct. Correct.
Şunu katılıyorum. Bizim yazdığımız, şu an yazdığımız bizim aslında çok da güzel bir fizik olmuyoruz. Yani sonuçta bu deneyimi yapabiliyorum.
Şimdi güzellikten ne kastettiğine bağlı. Şimdi ben bunun deneyini yapıyorum. Deneyde ölçtüğüm şeyler, the measurements that I make in the experiments are real quantities. But what am I measuring in the experiment? I'm measuring the eigenvalues. Now, the eigenvalues are always plus or minus h bar over 2. That is why I insist on using Hermitian operators to represent my observables. Because the Hermitian operators have this nice property that their eigenvalues are all real. That is one thing I'm measuring. The second thing I'm able to measure is if I can create a pure ensemble, I can measure the probabilities that the state representing that pure ensemble, the components of that state. But probabilities are, by definition, absolute values squared of the expansion coefficients, which are, by definition, real. Yes, correct, I'm using complex numbers to describe the kets of my state. Nevertheless, my formalism tells me that the probabilities are always real. And the measured quantities are always real. Now, complex numbers have nice, beautiful properties. Most of the time, to me, complex numbers in a larger group of real numbers appear more beautiful. Now, let us discuss some of the weird properties of quantum mechanics. Okay, so this is basically the way we proceed in a concrete example, the Stern-Gerlach experiment, and we have the silver atoms. Now, let's take let's say a more general case. Let's suppose we make a measurement of A. And the corresponding eigenkets, let's call them A. Then we make a measurement of B. And we call the corresponding eigenkets B. Or let's also label them. And then we have, let's say, a third measurement. We are measuring some other, it can be the same, some different property C. And let's call the corresponding eigenkets Ci. Now we can talk about the probabilities that given A, what is the probability that I will first measure B and then C? Well, given A, that tells me that initially, after the first measurement, I have the ket A. The probability that after this measurement, I will have B is just this number over here. This is the probability that once I know that my state is in the A ket, can be described by the A ket, the probability that I will measure a B is just this number squared. So after that measurement, I know that my ket is now a B ket. Then I can talk about the probability that I will be measuring a C. That probability will have this number. So this is the probability that once I measure A, then I measure B, then I measure C. Then let's construct this sum. Over all possible outcomes of B. I make a measurement, but I don't eliminate it. So you see, up to this point, in the Stern-Gerlach experiments, what we did was we made a measurement, we split our beam into two, we just picked up one of them, blocked the other one. So let's just assume that we don't do that. We make a measurement, we know which beam we are talking about, but we just sum over all the possible outcomes in the intermediate measurement. Now, classically speaking, if we were talking about classical physics, this would be equal to the probability that given A, we measure A first. So in all these experiments, we are saying that we are picking up a single value of A. The probability that it will be C. This is our classical expectation. Yeah, just you can think of this like this. Assume you have a bag full of, let's say, some, what do you like?
Marbles.
Some marbles. Which colors do you like in marbles? Blue. Okay, some marbles that are divided into 3 parts. Each part can have some color. Okay? We have a classical example. We have a bag full of marbles. Divided into 3 parts. And I label each one of these parts. Okay, so each part has a different number. So our first measurement, he just picks up one marble, looks at the segment 1, and he chooses the ones that are blue. Okay, so at the end of his measurements, he only considers those ones. I have a collection of marbles whose first segment is blue. Okay, so then measurement A. Pick segment 1 as blue. Okay. Then at the end of this measurement, I have a bag of marbles. All have segment 1 blue. Then, what is your favorite color?
Red.
Red. Okay, he makes another measurement in this marble set. And he chooses the red color. In segment 2. So at the end of this measurement, we have a bag of marbles, less. All have segment 1 blue, segment 2 red. Then the third measurement. So from here we moved here, then we moved here, then we are moving to the other page. Okay, the third measurement. Somebody else? Yes, what's your favorite color?
Green.
Green. So he picks up green. In segment 3. So now we have even less marbles, and all have segment 1 blue, segment 2 red, segment 3 green. Let's call this N3, the number of marbles over here, N2 here, and 1 here, yes, and the total number is N. Now the probability that we are talking about here is just, so we start with marbles with segment 1 blue. So we start with this one. A random marble in that bag, which will have segment 2 red, is nothing but N2 over N1. And among these, the number of red ones, no, the number of, the probability that any randomly picked one will have segment 3 green will be just N3 over N2. Okay? So this is the probability in this bag that a given marble has a segment 2 red and segment 3 green. But suppose let's do another experiment. We have this one, but in segment 2, in the second measurement, so we were picking up the red ones. He didn't pick up the red ones. He just looked at them, and whatever the color was, he put it back in the bag. He didn't make a selective measurement. He knows what color it is. So he made a measurement, but not a selective one. Whatever he measured, it just passed by. Again, we are talking about classical physics. So in that case, of course, N3 will be larger. The set N3 would be larger, but as your friend has pointed out, it will be as if he didn't make any measurement. So let me give some, N2 is the number of blue-red. N1 is the red ones, N2 is the number of blue-red, N3 is the blue-red-green. So this is if he picks up only the red ones. He makes a selective measure. He measures, and depending on his measurements, he puts it in a different bag or he throws it away. Or in a different experiment, not this one. Okay, so we are talking about two different experiments. One of them, first he prepares this bag of marbles. He picks one, looks at the color in the first segment, and if it is blue, he puts it in a different bag. If it is not blue, he just throws it away. So at the end of the first measurement, this is a selective measurement, he has a bag of marbles that are all blue in the first segment. Now there is this second measurement. He, in this bag, he picks up one randomly, looks at the second section, and if the second section is red, he just puts it in a different bag, and if it's not red, he just throws it away. And in the third measurement, he picks up a random marble in the bag that he prepared, and he looks whether it is green or not. If it is green, he picks it up. If it's not green, he just throws it away. This is one thought experiment. In the second thought experiment, this is what we do. We start as before. We pick up the ones that are blue in segment 1, but then he looks at segment 2. He sees that some color, whatever color it is, but no matter what color it is, he just puts it on his bag. So he doesn't make a selective measurement. He only knows what colors they are. And so basically, the bag that he prepares is identical to the bag that he prepares. And in the third measurement, he picks up the green marbles in this bag. But we could have just skipped him. I mean, he doesn't influence the result. So because whatever he picked up, he put it back. So if he had skipped him, nothing would have changed. So this is the process we are talking about now. We have these three measurements, A, B, and C. There is this intermediate measurement of B. He looks at it, but whatever the outcome of the measurement is, so that is why we are summing over all possible outcomes of the second measurement, it should be more or less the same. It should be the same, classically speaking. It should be the same as if B was absent. So we just jumped over B, measure A, and measure C. That is classical thinking. So is this point clear now? Let's see if this is actually correct. In quantum mechanics. So what we need to check is this one. This probability, we said that it is, we start with A, measure B, this is its probability. And after the measurement of B, we have the ket B, and we measure C. And this is its probability. So this is the left-hand side. If we ignore B, we don't make any measurement. Is this equal to? No, there's no sum, sorry. This is what we want to check. On the left-hand side, we have a sum over our intermediate measurements. On the right-hand side, we just ignore the intermediate measurement completely. Let's see if it works. Well, let's see, CA squared, this is nothing but CA AC. I know the identity. I can write the identity as in this form, summed over B. I can insert this identity over here and also over here. So this probability, I can write it as, well, I'm inserting two identities, so I have two sums. Let me just label one of them differently so that I will not be confusing those two sums. It is CB, BA, AB prime, B prime C. Now let's look at the B sum that we had over above. CB squared, BA squared. This is equal to, well, I have a single sum, CB, BA, but then I have AB, BC. Well, you see this term, these two terms give me CB squared, and these two terms give me the AB squared. That's my left-hand side. And you see, these two sums are not equal. So basically, this tells me that the act of measurement itself, whether we have a selective measurement or not, it changes the outcome. So let's go back to our Stern-Gerlach experiment. What do we really mean over here? And let's see whether our Stern-Gerlach experiment confirms this result that the act of measurement, the intermediate state, is changing our experiment, changing our result. Let's have a Stern-Gerlach in the Z. We have our beam. So we have these two splits into two. Well, we can just choose the plus state by just blocking the minus one. So this is our measurement A. Then we send it through our Stern-Gerlach experiment in the, let's say, x-axis. And then let's say we send it through our Stern-Gerlach experiment in the z-axis again. Now, this term over here, summed over the intermediate states, we first need to make the measurement. So we have to look where each silver atom is going through, whether it goes after this is A, this is B, this is C. After the B, whether each silver atom is going up or down. We have to follow them one by one. Well, following them one by one is basically the same thing as you block the lower one, so you know that it's going above. You send it through the second Stern-Gerlach apparatus. And plus, we are summing all the possible intermediate measurements. We are blocking the above one this time, so we know that the silver atom goes from below. So let's see, here we have 50% from the first beam, 50% above, and then it splits into two. So from the original plus beam, 25% goes above, 25% goes below. In the second experiment, again 50% goes below. Among these 50%, half goes above, half goes below after our third measurement. So 25% goes above, 25% goes below. So initially we have a beam that is pure plus. We first measure one by one. We first measure its property in the X plus, whether it is Sx plus or Sx minus. We first make that measurement. That it goes above or below. And then from these, we send them through the third measurement, which is identical to the first one. And again, the beam splits into two. So from the initial plus beam, in each one of these steps, 25% goes above, 25% goes below. So when I sum the two, what happens is from the initial beam, %50 goes above, 50% goes below. So this is when I make an intermediate measurement. I don't eliminate them, I just measure the beam, measure which way it goes. That's the only thing I do. Now let's eliminate the measurement completely in the intermediate, in the B measurement. If I eliminate it completely, so I have a plus beam. I send it through a Stern-Gerlach experiment in the z-axis. Well, it's a plus beam, so it should be deflected upward. None of them will be deflected downward. So 100% goes above, 0% goes below. So what I did, in the first setup, I measured the X component. I just let them pass through, but I measured the X component. Whatever the measurement of the X component was, I just let them through. But I made a measurement. In that case, the measurement itself, it erased all the information about the Z polarity of the spin. So since it erased all the information about the Z direction of the spin, when I pass it through a Stern-Gerlach experiment in the Z axis, it split into two, 50%, 50%. But if I don't make the measurement, all of it goes through the upper part, upper track. None of them goes in the lower track because it still carries the information about its the component of the spin along the z-axis. Yes. Well, okay, selective measurement is just choosing something. Here, well, in this setup, although I split my experiment into two, I don't actually need to separate it into two. I can, for example, the famous example is the double slit experiment with electrons. You can, if you want, track the electrons. You are not interfering with the setup. You are not saying, okay, in this, when I send this electron, I will only take if it goes from the above. You are not making this separation. You just track each one of them. And just the act of tracking it changes the probabilities. Again, as I said, here I just treat it as if I separate it as if I'm making a selective measurement. It's as if B is a selective measurement. It doesn't have to be. It's just for the sake of discussion, I'm treating as the combination of two selective measurements, but it doesn't have to be. So the definition of selective and non-selective measurement is you just select some states, let them go, and block the other ones. That is the definition of selective measurement. But here, so in a sense it's more clear over here, I'm not making any selection. I'm actually sending all possible outcomes of B. I'm just sending them through. But still, in classical physics, if you just send them all through, it's as if the experiment, that measurement is not done. Because measurement doesn't really affect the outcome in classical physics. But in quantum physics, the act of measuring, whether it's selective or not, it is changing the outcome. And the reason is the collapse. You see, if you want to describe this process in terms of the collapse, let's say we start with the plus state. That is our A. After B measurement, I know that the state is either Sx plus or minus. If I measure it, I know it. Well, the plus state is 1 over square root of 2 Sx plus, plus or minus, no, plus Sx minus. So if I make a measurement of B, I'm not selecting them. Just know which state is. This state collapsed to one of these. Now, after the measurement, I will know it, which one. But I just let them go by. I don't do anything else besides measuring. But these states are nothing but 1 over square root of 2 plus or minus states. So if I now send them to measurement 3, C, it will be 50% plus, 50% minus. I'm not blocking anything. I just look at its spin in the x direction, determine what its spin is, and independent of the outcome of the measurement, I just let them go by. That changes the result of the outcome. If I don't do the B measurement, I start with a plus pure ensemble. Well, it's a pure ensemble. It's still a plus pure ensemble. So it will be just 100% plus, 0% minus. If I don't do the intermediate measurement. So the measurement itself changes the ket through collapse.
O zaman bir öncekinde ortadaki deney olduğu zaman ya da olmadığını düşünelim ve function geri eski haline geliyor ki %50 ihtimali geri mi dönüyoruz hocam?
You see, which experiment?
Araya şey koyalım. Evet.
This one.
%50 ile başlıyor.
Well, you see, the problem with this sketch, let's say, is that it gives you the impression that we are doing two selective measurements. We are not doing selective measurements. We are just measuring. Okay, so if no more questions, let's give a 10-minute break so you can think over it a bit more, and then we can continue.